Okay, in this lecture, we're going to continue moving through our section 4.2 material on the column space and null space of a matrix and how they relate to a linear transformation. So in the first couple of parts of this section, we've introduced the null space of a matrix as the set of all vectors which are mapped onto the zero vector by that matrix A, and the column space of a matrix is the space which is spanned by the columns of the matrix A. Now that we've introduced these spaces, we might be curious about how the null space and the column space of a matrix are related to one another. So these spaces are fairly dissimilar in their definition, but we will see a surprising connection between the null space and the column space a little bit later in this chapter. And in this section, we'll start to look at some of the differences between the null space and column space. So in this first example, let's consider the following matrix A. It's a 2x4 matrix. So I'll make use of the dimension of it here in a moment. So let's keep in mind A is 2x4. And in part A, we are asked if the null space of A is considered as a subspace of Rk, what is the value of K? Or another way to ask this question is, for this matrix, in what dimension is the null space of A a subspace? So here, recall that the null space is defined as the set of vectors such that if I multiply A by that vector, I would get a zero vector. Now, since A is a 2x4 matrix, when I multiply any vector by this matrix, it must have 4 rows. And since we're talking about vectors, 1 column. So any vector in the null space would have to be a 4-dimensional vector. So here, the null space of this matrix A is a subset or subspace of R4. So the value of K that we're interested in here is 4. The number of columns of the matrix A. Now in part B, we are asked if the column space of this matrix A is considered as a subspace of Rk, what is the value of K there? So recall that the column space is the space spanned by the columns of the matrix A. And since this is a 2x4 matrix, that means that each column has 2 rows. So we're looking at a space spanned by 2-dimensional vectors, which would be a 2-dimensional space. So here, the column space of A is a subspace of R2. So the value of K that we're interested in here is 2. Now in part C, we're asked to find an example of a non-zero vector in the column space of A. So here, let's think about how the column space of A is defined. It is the space which is spanned by the column vectors of A. So let's maybe give these a name for reference. If we look back at our matrix A, we could call these column vectors A1, A2, A3, and A4. So column space of A is the span of A1 through A4, which is the set of all linear combinations of those 4 vectors. So if we want just one vector, one non-zero vector that lies within the column space, well, we could choose any one of these columns. So for instance, the first column vector, A1, is in the column space of A because one linear combination that I could take for my column space would be 1A1 plus 0A2 plus 0A3 plus 0a4. This would be a linear combination of my 4 column vectors, and therefore an element of the column space. And since a1 is a non-zero vector, we could use that as a representative from the column space of A. So here we have found a non-zero vector which lies in the column space. Now in a similar way, well, we could have chosen any of the 4 column vectors of A as a representative of the column space, or any non-zero linear combination of those column vectors would also be an example of a non-zero vector in that column space. So in part D, a little bit trickier. So in part C, we saw, well, it's very easy to find an example of a vector in the column space. Just take any of your column vectors. Now in part D, we're asked for a non-zero vector in the null space of A. So recall that the null space is the set of vectors x such that A times x is mapped onto the 0 vector. So we're trying to solve a homogeneous linear equation, or system of equations, with coefficient matrix A. So let's consider the augmented matrix for this equation. So our matrix A has a first row of 1, 3, 5, 0, and 0, 1, 4, negative 2. And we're augmenting that with the 0 vector since we're trying to solve for a homogeneous equation. So to solve this, we need to put our augmented matrix in reduced row echelon form. And here we see that in our first row, we already have a leading entry of 1 with a 0 below it. And in our second row, we have a leading entry of 1, which we can use to kill off the positive 3 that appears above it in the first row. So we could do that by taking row 1 and subtracting 3 times row 2. So our second row will remain as 0, 1, 4, negative 2, 0. And our first row becomes 1, negative 3 plus 3 is 0, minus 12 plus 5 is negative 7, and 6 plus 0 would be 6, with 0 plus 0 still being 0. So our matrix is now in reduced row echelon form. We see that columns 1 and 2 are our pivot columns, and so columns 3 and 4 will correspond to free variables. So let's write out our solution here. Looking at the components of a vector x, we see from our first row that x1 would have to equal 7x3 minus 6x4. Using the second row of this augmented matrix, we have x2 is equal to negative 4x3 plus 2x4. And then x3 and x4 are free variables. Our solution or solution set would be the set of vectors x of the form where x1 is equal to 7x3 minus 6x4, x2 is negative 4x3 plus 2x4, and then x3 and x4 were free. So if we write this as a linear combination of vectors where our weights are the free variables, we would have x3 times the vector 7, negative 4, 1, 0, plus x4 times the vector negative 6, 2, 0, 1. Where x3 and x4 could be any real numbers. So any vector, any non-zero vector that lies in that solution set, is what we're trying to find. We want a non-zero vector in that null space. So an easy way to choose an example of a non-zero vector would be to make some choice for the free variable x3 and x4, and an easy choice would be to let x3 equal 1 and x4 equal 0, in which case we would take as our non-zero vector in the null space the vector 7, -4, 1, 0. All right. Okay, so in this example, we see that for a matrix A, which is not square, so in this example, a 2x4 matrix, the null space and the column space are subsets of different vector spaces. In particular, the null space was a subspace of R4, whereas the column space was a subspace of R2. So these subspaces might live in different dimensions. And we can see here that to find, in part C and D, to find an example of a vector in the column space, well, it's a pretty easy process. We can just take any of the column vectors. But to find a non-zero vector in the null space, we have to solve a system of equations, which in general can be a little bit tedious. So a couple of differences that we're seeing between these two subspaces. So in our next example, we have a matrix A, which is 3x3, and a vector W, this 3x1 vector. And we are asked to first determine if the vector W is in the column space of A, and then determine if W is in the null space of A. So to determine whether W is in the column space of A, let's consider what we have to find. So here we would say W is in the column space of A if A times X is equal to W for some vector X in R3. So that is if I'm able to take a linear combination of the column vectors of A, where the weights are given by the elements of this vector X, and that's equal to the vector W, then that means W is in that column space. So in order to answer this question, we're seeing whether the matrix equation, A times X equals to W, is consistent. So let's consider an augmented matrix for that equation. So here our coefficient matrix A is 4, 0, 4, -8, -2, -9, and 6, 4, 8, which we are augmenting with the vector W, which was -2, 1, 2. So to simplify here, our first row has a leading coefficient of 4. Now to get a 1 there, I could divide my first row through by 4, but that would introduce a fraction on the right-hand side of our equation. But I do see that each entry in the first row is divisible by 2. So maybe to simplify a little bit at first, I could take half of the first row so that I would have 2, 0, 2, -1. Now, in this same first step, I'm going to try to eliminate the -8, that is the lead entry in my second row, and I see that I could use the 4 from my first row to accomplish that. If I take row 2 and add 2 times row 1 to that, we would have 8 minus 8 is 0. 0 plus -2 is -2. And then 8 minus 9 is negative 1. And performing the same operation on the right-hand side, we would have negative 4 plus 1 is negative 3. Now to simplify in my third row, to eliminate this value of 6, well, I could leave the third row alone for now and then make use of my first row. Or if I want to simplify a little bit here, I could take, for instance, row 3 and add row 2 to it, so that the leading coefficient will become a negative 2. And then I see I can use my positive 2 here to kill that off in the next step. So if I add row 2 to row 3, my third row becomes negative 2, positive 2, negative 1, and 3. So let's keep simplifying. So now that I have this 2 as the lead coefficient in my first row, I can use that to eliminate the negative 2 as the lead coefficient for my third row by taking row 3 and adding row 1 to it. So for now, I'm going to leave my first row alone. I have 2, 0, 2, negative 1. And I noticed that in my second row, all of the entries were negative. So maybe just to make all our entries positive, I could take the negative of row 2, or equivalently multiply row 2 by negative 1. And I have 0, 2, 1, 3. And when I add my first row to the third row, my third row becomes 0, 2, 1, 2. So now, in my second row, I have a leading coefficient of 2, which I can use to kill off the leading 2 in my third row by taking row 3 minus row 2. So my first row is now 2, 0, 2, negative 1. My second row I'm leaving alone as 0, 2, 1, 3. And my third row becomes 0, 0, 0, negative 1. So we see here from our third row, we have an inconsistent system. It's impossible for 0 to equal negative 1. So here the system is inconsistent, which means that there is no vector x such that a times x can be equal to w. Therefore, w does not lie in the column space of A. So we can say that the vector w is not an element of the column space of A. Now, the second part of this example asks us to determine whether W is in the null space of A. So recall that to determine if a vector is in the null space, we multiply the matrix A times W and see if we map to the 0 vector. So let's consider A times W. So that is the matrix 4, 0, 4, negative 8, negative 2, negative 9, 6, 4, 8, and we're multiplying by W, which is negative 2, 1, 2. So we get back a 3 by 1 column vector, where for our first entry, we have the dot product of our first row of A and the column vector W. So we have negative 8 plus 0 plus 8 gives us 0. For our second row, we take the second row of A and the column vector W and consider their dot product. So here we would have 16 minus 2 is 14, and then minus 18 leaves us with negative 4. So at this stage, once we find that that second entry of the product is non-zero, we know that this will not yield the 0 vector, and so the vector W is also not an element of the column space of A. The null space of A. Now, we only need to find one non-zero entry of that product vector, but if you consider your third entry as the third row of A, take in the dot product with the column vector W, you have negative 12 plus 4 plus 16, which leaves a positive 8. But again, as soon as we see that our product is anything other than the 0 vector, we know that W does not lie within the null space of A.